Section 5.5, Day 1, Complex Numbers and Roots. Please write down the essential question. How do I use imaginary and complex numbers to solve quadratic equations with complex roots? Recall in section 5.3 and 5.4, we were solving quadratic equations and finding, you recall, let's highlight this, the roots, which were the zeros, which were the x-intercepts. Those were real solutions. A parabola was formed that intersected the x-axis at 2 points or had a vertex on the x-axis if there was a double root. We are now going to find the non-real solutions, which means the parabola will not intersect the x-axis. We can't call them x-intercepts. You can see in the graph of f of x equals x squared plus 1 below that f has no real zeros because it doesn't intersect the x-axis. If you solve the corresponding equation, this is what happens. That means it has no real solutions. There's a negative under the square root. However, you can find solutions if you define the square root of negative numbers, which is why imaginary numbers were invented. The imaginary unit I is defined as the square root of negative 1. So I equals that. You can use the imaginary unit to write the square root of any negative number. So we're still calling them solutions. We're still calling them roots, but they're really non-real because they will not intersect the x-axis. An imaginary number is the square root of a negative number. Right here is what I just wrote down. Imaginary numbers can be written in the form bi, where b is a real number and I is the imaginary unit. The square of an imaginary number is the original negative number. That makes sense. So if we have I is equal to the square root of negative 1, and I say to you, square both sides, that is I squared. If you square a radical, the radical goes away, and out comes that. So these are important things that you are going to want to remember. I equals the square root of negative 1, and I squared then would equal negative 1. Example 1, express the number in terms of I. So number 1, we can bring down the 2, and we can break this up into the square root of negative 1 times the square root of 36. And we know already that that is I. This is times, and that is 6. So 2 times 6 is 12I. It's not plus or minus because we have an expression where we don't have an equation like x squared equals 25, where we take the square root of both sides. Remember, when you take the square root of a square, that cancels. When that comes out, you get 2 answers. That's not what's happening here. Example 2, again, the negative underneath, or like that. That's I, root 12. Well, we can break up root 12 into the square root of 4 times the square root of 3, and the I still has to come with it. I comes down, square root of 4 is 2. So then how we write that is 2I root 3. Example 3, solve the equation. Well, here we go. We have an equation now. We know to take a square root of both sides. That 2 cancels, the x comes out. I know I'm going to get a plus or minus. And I can break that up into the square root of negative 1 times the square root of 36. That's I. That's 6. So x is equal to plus or minus 6I. If you wrote it X is equal to plus or minus I6. That's fine too. I usually like to put the number before the I. Example 4. Well, I can't take a square root yet. I have to move the 48 over to this side. So now now the x squared is by itself. So now I can take a square root. We can break that up like that. That's I. So let's see. Two numbers that multiply to 48. One of them being a perfect square, 16 and 3. That's 4. 4i, root 3. And there's our plus or minus because we're solving an equation. Example 5, we're going to save for class. Now we're on to something a little different, but we're still talking about the I, imaginary numbers, which is called a complex number, is a number that can be written in the form, let's highlight this, a plus bi. The important thing is a and b are real numbers, and I is the imaginary number. The set of real numbers is a subset of the set of complex numbers, C. So if you look over here, if I talk complex numbers are made up of real numbers and imaginary numbers combined. Every complex number has a real part and an imaginary part. Okay, so up here we said A and B are real numbers. Yes, they are. But now we're talking about the real part and the imaginary part of a complex number. This whole thing is a complex number. The real part, that is A. The imaginary part, that is B. So when you're asked what's the imaginary part, you don't say BI, you just say B. It's called an imaginary part because you're taking a real number times an imaginary number, which makes it an imaginary part. Two complex numbers, A plus BI, are equal if and only if their real parts are equal and their imaginary parts are equal. Example 6. Find the values of x and y that make each equation true. Okay. Well, let's go back a minute. Right here, we're going to use this. Two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. So here are the real parts, and the imaginary part is the -6 and the 20y. So I can set 2x equal to -8. X is -4, and I can set -6 equal to 20y. Let's see, 2 goes in there 3 times, 2 goes in there 10 times. They want us to define x, and we did, and they wanted us to find y, and we did. And how we found them is we set so notice, before I say that, here's our little divider between our two sides, our two complex numbers. We set the real parts equal to each other and the imaginary parts equal to each other and solve for x and y. 7 we're going to do in class, and here are your video questions.